Hello everybody, welcome back. We're about to begin section 6.3 in the text, where we're going to start looking at some properties of trigonometric functions. Not just this section, but there are going to be a lot of other sections as well, but we're going to go looking at the most basic ones. So before we begin, let me just remind you that the two most basic trig functions, sine and cosine, are really just defined to be the coordinates of a point on the unit circle that corresponds to the angle in question. In fact, you take an angle theta, see the angle with this and a ray, the ray coming out of the origin makes an angle theta with a positive x-axis, and it corresponds to a unique point on this unit circle, and the x-coordinate is cosine theta and the y-coordinate is sine theta. And just to show you, I really want you to familiarize yourself with the values of sine and cosine for important angles. And I actually sent you a copy of this unit circle, which lists the most important angles, or at least the values of trig functions for the more common angles like 30 degrees, 45, 60 degrees, and so on, and then you can see that this is supposed to be symmetric. So once you know that one's in the first quadrant, you can use symmetry and find these other points and all the other coordinates. So I would say, even though you'll obviously have access to this when you're taking quizzes and exams, but you want to memorize this, okay? And really, you just have to memorize the ones in the first quadrant. Remember, pi over sig. Wrote here the angles in radians, but if you want to, you can also write them in degrees if you want. I'll let you finish up the rest of these. Okay, so we know that for example, the cosine of 30 degrees is going to be square root 3 over 2, and the sine of 30 degrees is 1/2, and so on. Okay, so that hopefully helps. Okay, so we're going to develop a few properties and even some identities here, and it's going to look like a lot of stuff being thrown at you, but in a way we're just, of course, stating the obvious, okay, from this picture here. Okay, first off, because we have the unit circle, it's the circle of radius 1 centered at the origin. So every point, you take any point on this circle, and its x coordinates is always going to be between -1 and 1, and the y value will also be between -1 and 1. And so therefore, it makes sense that the cosine and sine of theta are bounded between -1 and 1. Okay, that's hopefully obvious. The fundamental identity is given by this, and all we have is, because the x-coordinate is cosine and the y-coordinate is sine, if we substitute x equals x with cosine theta, and if we substitute y with sine theta, we just get this. So that's clear as well. Now, the only thing here is the notation. And we really, instead of using this notation, we will bring the 2 in here, or the exponent. And in general, the situation is, if we have a trig function like cosine k raised to the kx, this is the same thing as saying cosine of x raised to k. Okay, we use this notation because if we just write this, it's unclear whether it's unclear whether this exponent applies to the x or cosine x. So it could be that we might mean something like this. All right. In general, what you don't want to do is write something like this, because I won't know which one what you're raising to the k power. Okay. So that's why we use this notation here. Okay. So that's why the cosine squared plus sine squared is 1. Another property that we hope is kind of obvious is the cyclicity, or the periodicity, of these two trig functions. That is, if we take this angle and we add 1 revolution to it, we get the same point. So we're going to get the same x-coordinate and the same y-coordinate, and then the cosine and sine will be the same. So, and we'll remember 1 revolution corresponds to 2 pi radians, or 360 degrees. So that's why if we replace theta with theta plus 2 pi, or if we're in degrees with theta plus 360 degrees, we get the cosine and the sine are unchanged. And then what this means is the cosine and sine, these are functions, or I would say they're periodic because they repeat this every 2 pi units, and we say the period is 2 pi because this is the 2 pi is the smallest possible period it has. Okay, it's basically the length of the smallest cycle. Okay, so in your text they actually give you the definition of a period, what it means for a function to be periodic. We also see that if theta is in the first quadrant, the x and y coordinates are both positive, so that means the cosine and sine are both positive. In the second quadrant, we see the x coordinates are negative and the y coordinates are positive. And in the third quadrant, we see the x coordinates and y coordinates are both negative. And in the fourth quadrant, we see the y coordinate is negative and the x coordinate is positive. So that's how this comes about. And it's hopefully you can see it's not that big a deal. When we say theta is in the first quadrant, obviously, let's say that certainly means that theta is between 0 and pi over 2, or 0 degrees and 90 degrees. However, there could be theta could be in a different range and still be in the first quadrant. For example, let's say if you take 365 degrees, okay, that would be in the first quadrant, right? Okay, it would just be 1 revolution plus 5 degrees. Okay, so hopefully you kind of understand what we mean by theta is in the first quadrant. That just means the corresponding point on the unit circles in the first quadrant, and so on. Then we also have this property, which says that if we replace theta with minus theta, we get the same thing if we were talking about we're taking cosines, and we get the opposite if we're taking sines. And the reason for that is as follows: if we take theta, we take this point here and we rotate it counterclockwise through an angle of theta, and then if we do the same thing and we rotate it clockwise, we see that these 2 points are always going to be opposite each other, opposite across through the x-axis. So the x-coordinate is going to be the same, and the y-coordinate is going to be opposite. So that's why because the y-coordinate is always the opposite, we have minus sine of theta here. And then this also means that cosine of minus theta is just equal to cosine theta. So that's why this works. Okay. All right. So let's look at a couple other things to keep in mind. We kind of talked about this last time. The cosine of theta is 0. Well, when is it going to be 0? It's going to be 0 when the x-coordinate's 0, and that's going to be here and here. Well, this corresponds to pi over 2 radians, or 90 degrees. This corresponds to minus pi over 2, or minus 90 degrees. You could also say it's 3 pi over 2. Okay, that would work too. Just this would be pi over 2. This could be 5 pi over 2, 7 pi over 2, and so on, right? But it's basically these 2 points where the cosine is 0. Okay, so that's why you can say that the cosine of theta is 0 when theta is either pi over 2 or minus pi over 2 plus some multiple of pi, 2 pi, where k is just an integer, meaning k is 0, 1, 0, 1, negative 1, 2, negative 2, and so on. If you're using degrees, what this means it's plus or minus 90 degrees plus some multiple of 360 degrees. More generally, another way of thinking about this is really just, you could also say this is just, let's say L pi over 2 where plus or minus L pi over 2, where L is odd. Okay? So you can also think of it that way. Now, when is sine equal to 0? Well, that's going to be when the y-coordinate is 0, and that's going to be here and here. This point corresponds to theta equaling 0, or 2 pi, or 4 pi, or any even number times pi. Okay, and we also have here it's pi, 3 pi, 5 pi. Okay, you could also take negative values, negative pi, negative 3 pi, and so on, right? In both of these cases, we were talking the angle is a multiple of pi. Okay, so when the angle is ever a multiple of pi, you're going to end up here or here. So that's why sine of theta is 0 when theta is a multiple of pi, okay, or a multiply of 180. So we want to keep that in mind because we'll be worrying about that later. Number 7 just basically formalizes everything just with different notation. Okay, so if you remember for when we're talking about functions, the domain of a function is the set of all things that can be possible values you can plug into a function, the set of all inputs, and the range would be the set of all outputs. So because we can take the sine of any angle, right? We can just whatever theta is, we can wrap it around the unit circle theta many times, and we'll get a point, and then we'll get a cosine and sine. So the domain of both the sine and cosine are all real numbers. And the range, of course, we already said the sine and cosine have to be between -1 and 1. So the range is this closed interval, all numbers between -1 and 1 inclusive. C is just a fancy way of saying that sine and cosine are periodic for period 2. All we're doing is we're just saying this. Okay. Just restating it. And in fact, we can go, because of it being periodic of period 2, if we replace x with x plus any multiple of 2 pi, that leaves the functions unchanged, right? And then f and g, if f is cosine of x, or rather if f is sine x in this case, sine of x is odd, meaning that f of minus x is equal to minus f of x, and g and cosine is even, because cosine of minus x equals cosine of x. Okay, if you remember from Math 128, we talked about even and odd functions. Okay, so in that, this is basically the definition of this is an odd function, this is an even function. So that's all we're doing here. Okay, so hopefully that's not too bad. I want to just do a few examples now. See how we can do this. So if we wanted to find the sine of 405 degrees, basically we'd like to replace this with a number that's either between, well, because we're in degrees, we'd like to replace it with a number between 0 and 360. And we can know that 405 can be written as 360 plus 45, right? So this is the same thing as the sine of 360 plus 45, and this is the sine of 45 degrees. Okay, so this is root 2 over 2. Okay, you can read that either by memorizing or looking it up on your unit circle. Let's look at this. Hopefully you can read it. I meant to say 32 pi over 3. 32 over 3 can be written as 30 over 3 plus 2/3, right? So this is going to be, this is the same thing as 10 plus 2/3. So this can be written as the cosine of 10 pi plus 2 pi over 3. And 10 pi is a multiple of 2 pi, right? This is the same thing as 5 times 2 pi. Okay, so this is just going to be the cosine of 2 pi over 3. Okay. Okay, which, again, if you look at your unit circle here, 2 pi over 3, okay, the x-coordinate is negative 1/2. So this is negative 1/2. All right, let's look at something where we use the fundamental identity. So let's say find the cosine if sine of theta is 1/3 and theta is in quadrant 2. Okay, we'll see why the quadrant is important in a minute. But we know that, again, sine squared plus cosine squared of theta is equal to 1. Okay, and in this case, the sine is 1/3. Okay, when you square 1/3, we get 1/9. You can subtract 1/9 from both sides. So the cosine squared of theta is 8/9. And then you can take the square root of both sides. So we get cosine of theta. Well, normally we would say plus or minus 8/9, the square root of 8/9. But this was where in quadrant 2, the cosine is negative, right? So we're just going to use the negative square root. So it's negative square root of 8/9. Okay, and if you wanted to, you could write this as negative square root of 8 over 3. Okay. All right. Yeah, just remember this is the same thing as saying cosine of theta squared. Okay. So that's how we go from here to here. Let's do another example. If we have we want to find the sine of theta if the cosine of theta is 5/13. So in this case, sine squared plus cosine squared of theta is 1 again, and looks like it really doesn't matter if you say sine squared plus cosine squared or cosine squared plus sine squared. We know that it means that it's the same thing. This is just sort of how I think of it. So cosine of theta is 5/13, and sine is what we're solving for. Okay, so sine squared of theta is, or plus, this is 25 over 169, and this equals 1, and 1 can be written as 169 over 169. And you can get, now that we have a common denominator, we can subtract 25 over 169 from both sides, and we get sine squared of theta is 144 over 169. Okay, we can 169 minus 25 is 144. And then, so sine of theta is going to be plus or minus the square root of 144 over 169. And because we know the sign's positive, that means we take the positive square root. The positive square root, and the square root of 4 and 44, usually these will not be a very nice number, but 12 squared is 144, 13 squared is 169, so this is 12/13. So that's the sign in this case. Okay, a few more examples. Cosine of negative 120. Because cosine is an even function, the minus sign can just go away. And 120, that's the same thing as 2 pi over 3, and once again we checked, we just saw that at 2 pi over 3, this is the same thing as 120, and the cosine is negative 1/2. Okay. The sine of negative 3 pi over 2. Sine is an odd function, so the minus sign comes out. And 3 pi over 2, of course, that's down, corresponds to this point. The y coordinate is negative 1. So this is going to be minus -1. And now the minuses cancel out. We just get 1. Okay. The sine of 19 pi over 4, or negative 19 pi over 4, this is pull the sign out. Okay. And let's see if we can write this as 2 pi or something times 2 pi plus something else. And in fact, we can write this as 16 pi over 4. 19 can be written as 16 plus 3. Okay, 16 divided by 4 is 4. So this is 4 pi plus 3 pi over 4. And this is a multiple of 2 pi, so we can just sort of ignore it. And this is just going to be minus sine of 3 pi over 4. Okay, and negative 3 pi over 4. It's right here. And we see the sine is root 2 over 2. So this is going to be minus root 2 over 2. Okay. 17 pi over 6. We're going to cosine of that. Okay. This, let's see if there's no minus sign here, so that's nice. Can we write this as 2 pi or some multiple of 2 pi plus something? And the answer is yes, because 12 pi over 6 is 2 pi. Okay, so we can write this as cosine of 2 pi. Okay, 17 can be written as 12 plus 5, so this is going to be 5 pi over 6. Okay, so this will be the cosine of 5 pi over 6. Okay, and if we look at our unit circle, cosine of 5 pi over 6, the cosine is minus root 3 over 2. Okay, so yes, I know, it seems so easy when the professor does it, right? So I'll let you do some of the homework problems, get lots of practice, and in the next video we'll be talking about the other 4 trigonometric functions and see how they relate to all this. Thanks. See ya.